Welcome to the R Lab for Chapter 3, talking about linear regression. So here we have our R Studio in the upper left-hand window. I've opened the Chapter 3 lab, and so we're going to start executing some of these commands. So first we want to load our maths library and our ISLR library into memory, so we have the data sets that we're going to be using. The first command I'm going to call here is fix on the Boston data. And so what this does, it allows us to open the Boston data in an editor, allows us to browse the data, and if we needed to fix some of the data values, if there was a data value that we thought was absurd, we could just replace it with some values that we wanted that we thought would be better. These are fine values, and I certainly don't want to change them. And then we can save or just close this, and then it'll load the Boston data as we've edited it, possibly cleaned it up, into our workspace. The Boston data is a data set that provides data for neighborhoods in Boston. And so there's 504 neighborhoods that are covered. And if we do $Boston in R, we'll get the documentation for the Boston data. And so this is suburbs in Boston, in particular looking at housing values. And so there are a number of variables. There's the crime variable, which is the per capita crime rate by town. And since this is the first time we're using the Boston data, it's important, worth time for us to walk through it. ZN, which is the proportion of residential land zoned for lots over 25,000 square feet. Industry variable, which is a proportion of non-retail business acres per town. There's a CHAS, which is the Charles River dummy variable, and it's equal to 1 if the tract for the housing community bounds the river, and it's 0 otherwise. I went to graduate school in Boston, and the neighborhoods along the Charles River were beautiful. Charles River is beautiful, and so the ones there you would expect would be worth more. We have a NOx variable, which is the nitrogen oxides concentration. RM, which is the average number of rooms per dwelling, so a room variable. Age, which is the proportion of owner-occupied units built prior to 1940, so that's going to measure the age of the houses in the neighborhood. Higher value there, higher proportion corresponds to older homes, or at least more old homes. DIS, which is a distance to the 5 Boston employment centers. So you would expect a lower value of DIS would correspond to higher house values. RAD, which is an index of accessibility to radial highways. Traffic in Boston is horrendous, and so being close to a highway would certainly increase the value for homes in a neighborhood. Tax, which is the full value property tax rate per $10,000. This is not the amount of tax, this is the tax rate. So a higher tax rate you would expect would make lower value homes, but on the other hand, neighborhoods with high value homes might have higher tax rates. So that may be something that people are using to measure because it's going to be based on the home values. PT ratio is a ratio of pupil to teacher ratio. Black is a measurement of the ethnicity in people in the different housing developments or neighborhoods. And LSTAT is the lower status of the population. So it represents the percent of the population that is in a lower socioeconomic status. And MEDV or MEDV is the median value of owner-occupied homes in the thousands. So we're going to look to try to predict the median value of owner-occupied homes based on a number of the other variables here. In particular, we're going to start by looking at LSTAT, the percent of the population that has a lower socioeconomic status. And for reference, this data goes back to the 70s, so we're going to see house values that don't represent what you would expect them to see today. So let's execute some of our commands. So this command lm.fit, we're going to build a linear model, and we're going to fit it, and we're going to fit the median value as a function of LSTAT. And when we try to execute this, we're going to get an error that's telling us in this error that median value is not found. That's because we haven't assigned any data. It's told it what data frame to get median value from. So this command tells it where to get the data from. We're going to get the data from Boston dataset. This command tells the workspace to attach Boston. So once we've attached Boston, we can execute this command the way we have it, and we will it'll execute without error because we've already told it to use the Boston dataset. Now we've built our linear model. We fit our linear model. It's median value as a function of LSTAT, and we can take a look at that linear model. The coefficients for that model, coefficient for the intercept is 34.55. That tells us if LSTAT were 0, if the percent of the population that were in the lower economic status were 0, then we'd expect the house value to be 34,550. And for each increase in 1 in the lower socioeconomic status, median house value goes down by $950. We can look at a summary, and so this will give us more information about our linear model, information about our residuals, information about our coefficients, the estimate for the coefficient, standard error, t-value, and then measure of the significance. 3 stars tells us at what level of significance we can consider our variables. Both are very significant. And then additional information, f-test, degrees of freedom, and so on and so forth. Going back to our commands in this lab, we can look at the names of everything that's associated with the LM fit. So we can reference variables that are in LM fit this way. And that'll tell us the coefficients. It's more robust to access that same information, coefficient, LM fit, in that way. And we can look at coefficient intervals for LM fit. So these are intervals for those coefficients, and we can look at prediction intervals, confidence intervals, and prediction intervals. And so this tells us if LSTAT is 5, 10, or 15, and then we get the confidence intervals. So this tells us the lower and upper confidence intervals for what we expect this value to be on average for LSTAT of 5, and then 10 and 15. And then here we're looking at prediction intervals, which tell us if this would be the predicted median house value in a neighborhood with an LSTAT of 5, and then 10 and 15 as well. And then this interval prediction tells us the lower and upper bounds for the interval of prediction. So this means that 95% of the time, median house value with an LSTAT of 5 is going to be within that range. We can plot the LSTAT versus median value, and we can see, as we expected, when LSTAT's low, when a low percentage of the population has a low socioeconomic status, that's going to correspond to higher median values. We can plot a fit from our linear regression. That line is rather thin, it might be hard to see, so we can plot a thicker line, or slightly better, we can plot it in red. And so there's our line from our linear regression. One of the things we'll notice when looking at this plot, at the lower LSTAT values, we're underestimating, and at the higher LSTAT values, we're also underestimating, right? The median value is not going to hit 0 because you have a 35% lower socioeconomic status. So we have some measurement of where the errors are occurring, and there's some apparent nonlinearity in this model, in this relationship. The model's linear, the relationship appears to be nonlinear. We can take a look at a couple of different ways to plot the data. We can plot it using different colors. different icons, small filled circles instead of large open ones. We can plot the data with pluses. Here's a list of all the different icons that you can use in R. Now we're going to put together 4 different plots on the same screen. So this par mf row command, that tells us we're going to create a 2x2 array of plots down in our plotting window. And now we're going to plot the linear model, and we're going to plot 4 standard plots. And to see these better, we'll click on zoom. So we'll open these plots in a larger window. One of the things we'll observe, we look at the fitted values on this axis and the residual. The residual is the difference between the fitted value and the actual value. And we see as we get to large fitted values, if our predictions are in the larger range, then we have larger residuals. And similarly, if the fitted values are very small, meaning the prediction of our median house value is small, we also get these larger residuals. And that suggests that there's some non-linearity in that relationship. This red curve is a sliding average of those values. Other plots represented here also suggest there's some non-linear relationship going on. Here are some other commands that would allow us to plot those residuals just as we had before, and then studentized residuals, and then hat values. So let's take a look at this. Here's our hat values, and this acts as indices, and so we see particular data points that have large hat values. And then this is the residuals as a function of prediction, exactly what we saw in the previous zoomed in plots. And then here's a studentized residual. So the plots, these 2 plots, top left and top right, are similar, and the only difference is the standardization of the y values in that plot. This which max command tells us which data values here in its index 375 give us the maximum hat values. Okay, let's talk about multiple linear regression. Now we're going to build a linear model, and we're going to fit median value as a function of LSTAT and age. So we're doing regression median value against 2 predictor variables, and we can get our summary of that linear regression. So first in the summary, we're told what the regression is. We're given residuals and then the coefficients. So the estimate, this is a median house value if the other variables were equal to 0, if the age was 0, if there were no old houses. And what we see is that as LSTAT increases, housing price goes down, and as age increases, housing price goes up slightly. And all of our variables have some level of significance, with age having the lowest significance. Let's do a multiple linear regression using all the variables. And when we use all the variables, we get our residuals and our coefficients. When we look at our significance level and our t value, the one thing that's of interest here, age, I'll go across, has a very small t, a very large p, and has no significance. So age seemed like it might have been significant when it was by itself, but when we incorporate these other variables, age becomes insignificant. So we probably don't want to use age in this model. There is a nice command in R that will allow us to rebuild the model and remove age. Before we do that, we're going to load the car library and look at the VIF values. These measure the collinearity, multiple collinearity in the data when they're large, as it is for example, text. That tells us that text has more collinearity with the other variables. Generally, if this value is 5 or more, then it's considered high. 1 is the lowest value you can get, so this CHAS variable is not collinear with a lot of the other variables. And text and rad are the variables that have the highest collinearity, which tax might be reasonable that it's collinear with a lot of variables because that would be determined by possibly a lot of the other demographic variables that we have here. Okay, so let's go back to our model. We're going to rebuild the model, but we're going to remove age. Putting this dot minus the dot here is how we're going to build the median model with median value as a function of everything, and then minus age means we're going to remove age from this model. And if you look at this model, it's going to be a slightly better model if you look at some of the metrics for the model, and we no longer have age included. This creation of the model by removing age, we could do the same exact thing by saying we're going to take our fitted model and we're going to update it with this command. The last thing we're going to take a look at is interaction terms. And so we're going to make a linear model median value as a function of LSTAT star age. And that says we're going to include the LSTAT variable and the age variable, and then LSTAT time age. So that's what this star is shorthand for in R. And then we're going to get the summary for that model with the interaction terms. So that model says, right, gives our call, our residuals, and our coefficients. We're provided with LSTAT, and we're told that's significant. Age here is not significant, but LSTAT times age is significant. So that LSTAT times age may capture some of the nonlinearity that we're seeing in our variables. This concludes our walkthrough of the first part of the R lab for chapter 3 of the textbook. Thank you very much for watching.